Okay, this is section 2. We all in it together? Okay. So I want you to hear this. I'm going to tell you every single day probably. This chapter has vocabulary. And you are going to have to keep all these terms very clear in your mind. These are all about different ways to look at right or at triangles and what happens when we create some segments within the triangle. Okay, you're going to want to have your note cards so that you have, because we're going to be adding some things to it. So the first thing that you should have from this chapter was the mid-segment theorem, correct? Okay. So again, this is about vocabulary and knowing what is going to be congruent in these triangles. Okay, so you're going to want to do a lot of review every single night. Okay. All right, so the first thing that this section talks about is a perpendicular bisector theorem. So that's the first theorem that you're going to want to have in your note cards. Okay, we're going to talk about the terminology. Because don't just memorize perpendicular bisector. What exactly is a perpendicular bisector? What? No, I'm just asking you the question right now. You can add it later on if you don't know. But when I say a perpendicular bisector, what do those two words mean? Kaylee? So we should be looking for two things. If we are trying to determine if we have a perpendicular bisector, we need to look for two pieces of information. Does it cut the segment into two equal parts? And is there a 90-degree angle? Because if it just cuts it in two equal parts, we don't know that it's a perpendicular bisector. Do you all agree? Okay. So if I give you the perpendicular bisector theorem says, given a segment AB, if I put a perpendicular bisector through that segment, I'm calling CP, okay? So I know that it's perpendicular because I'm showing the 90-degree angle. I know that it's a bisector because these two symbols indicate that my lengths are the same. Then, if I put a point on that perpendicular bisector and draw the lengths to each endpoint, the perpendicular bisector theorem says those lengths are congruent. Okay? So, perpendicular bisector, hi. Hold on. So, again, perpendicular bisector, these two lengths will always be congruent. So that's what you want to do. Now, when you're putting these on your note cards, I don't want just the words. I want you to have a picture there. So when you draw this picture, get out another color pen. And what I want you to do is to do what I did. I made the perpendicular bisector and the line segment one color to indicate that these lengths of AP and BP are the ones that we gather to be congruent. So kind of color code it so that you know what is being congruent from that statement. Okay? It's going to be something visual as well as the words to all help you keep it organized. All right. Then the converse is the next one that you want to have. Okay? This is the next one that you're going to want to have in your note cards. And you know the converse simply means the opposite, right? So the converse of the perpendicular bisector theorem says if we have a line segment and we put a point outside, so here we have a line segment AB, and I put this point P out here, if I connect and create a triangle to these endpoints and I indicate that they are congruent, then we know that P will fall on a perpendicular bisector. So I'm not showing you that if I extend segment CR all the way that it will intersect P, but we know it will given that AP and PB are congruent lengths. Does that make sense? All right, any questions on those two? Okay. So let's look at this problem. this says, I'm telling you, LN is the perpendicular bisector of MK. LN is the perpendicular bisector of MK. That means there's a right angle here, and I can cut the lengths into 2 equal parts. Find LM. Find the length of LM. What am I going to do? I'm telling you, LN is a perpendicular bisector. What am I going to do, Hannah? Because the perpendicular bisector theorem says if we cut this length into 2 equal parts and form a right angle with a perpendicular bisector, these 2 lengths must be congruent. Agreed? Okay? Well, then that just tells me that -9 is equal to -2x. So x is equal to 9/2. Did I answer the question? What's the question asking? What's the length of LM? All right, so we got to substitute it back in. So we're going to say that LM is equal to 6 times 9/2, which is 27 units. Okay? Probably, we're talking about lengths, yeah. All right, question 2. Is point O on the perpendicular bisector of LN? Some say yes, some say no. How many of you think it is? Raise your hand if you think it is. Okay. How many think it isn't? How many don't know? Okay. So I've only got two theorems to use, right? One is the perpendicular bisector theorem and one is the converse. Which one am I going to think about using if I'm looking to see if this point O would fall on the perpendicular bisector LN? Okay, so what does the converse say? The converse says that if the point out here to either side is what? Congruent, then it'll fall on the perpendicular bisector, correct? Are these lengths congruent? So, is O going to fall on the perpendicular bisector? Because of the converse of the perpendicular bisector. So it's no, because KO does not equal MO. And that's the converse. Converse of the perpendicular bisector theorem. Okay? Making some sense? All right. So, these questions aren't just do you know the theorem, can you apply them? Then you really, truly know them. Okay. So, I drew this all for you. Circumcenter, another thing that you want to put onto your note cards. There's some things that you want to know about the circumcenter. And I'll tell you in a second what I want you to put on it. Okay, other than that I want circumcenter. Okay, circumcenter. A point in, on, or outside of a triangle. It's where all the perpendicular bisectors meet. So, I have 3 sides of a triangle, correct? I can draw 3 perpendicular lines, one from every single side. Does that make sense? Okay. This is an obtuse triangle because it has one angle greater than 90 degrees. So when we connect all the perpendicular bisectors, in other words, this segment here is a perpendicular bisector. It is perpendicular to this side of my triangle, yes? Okay? This side, here's the perpendicular bisector. It divides this side into 2 equal parts. Yes? And I'm defining this one to be perpendicular and dividing it into 2 equal parts. I'm telling you that's what I created it. Okay? All right? So it's perpendicular to the side that it intersects. Careful. For example, this line is intersecting the two sides, right? But it's only perpendicular to one. Okay? This point right here is the circumcenter. Now, what's interesting about the circumcenter is that once we've defined where that point is, when we take lengths from this point to all the vertices, those lengths are congruent. So again, we create the circumcenter by finding all the perpendicular bisectors. We find that point, and we draw from that point to all the vertices of the triangle, and those lengths are the same. Okay? Athena. So in other words, this side is divided equally, but it's not necessarily equal to any of the other portions. Okay? Did you follow that? So this is an obtuse triangle, and where does the circumcenter fall? Well, just outside. Outside. Okay? Then we have a right triangle. Again, we're going to have three perpendicular segments. And in a right triangle, so if you can look up here and just follow me. Here is my perpendicular bisector to this side. Here is my perpendicular bisector to this side. Just perpendicular to that side. That's just kind of coming, it's just kind of getting cut through the triangle. Okay? All right, then here, if you see this one right here, that's perpendicular to this side. Allie, that's probably what you were asking about. Okay? So we have three perpendicular bisectors. Where is the circumcenter falling in this case? Where? On the hypotenuse. So on a right triangle, the circumcenter falls on the hypotenuse. Hypotenuse. Okay? So then remember, from that point to where? The vertices. So from here to here, and from here to here, and from here to here. Now I curved them so that you would see. We're really talking half of the hypotenuse, aren't we? Okay, but I'm curving it so that you can see what I'm indicating. So this length, and the green ones are all congruent. This is why you're going to want to have some different colors so that you can see which ones are congruent. You've got a lot of line segments going on. You've got the perpendicular segments, and then you've got the congruent segments. The perpendicular segments are not equal. Yes? You'll do one for all three. Yes. Okay. Can I move on? All right, the last one is an acute triangle. And where is the circumcenter falling in this case? Okay, it falls inside the triangle. So what I want you to do is I want you to indicate perpendicular angles, sides that are divided in half, and then in a different color, show me the lengths that are congruent in that triangle. Abby? Somewhere inside. Acutes are always inside. Obtuse is always outside. Right, always on the hypotenuse. Natalie? So the bisector lengths are all of different lengths.
But as I said, if it's a bisector, if there's one through, is it still the entire line? Like, how do you show that?
Show me. Maybe you can show me. Is it up here that you can talk to me about it? Come on up and show me what you're talking about.
Since, you know, like, it's like that.
Yes.
Is this and this entire line
Divided into half. Yes.
Okay.
So the side of the triangle that you're drawing the perpendicular bisector. Right, they don't. They're just being extended. Yeah, does that help you now? Okay. All right, so what we should have is what Natalie drew. This one, divide this side in half, right? And then here's your third one. And that looks like that. Okay, so now, where am I? So here is my circumcenter. Would you agree? Okay. Where am I drawing? From that point, what do I draw to? The vertices. This length, this length, this length. Those red lengths are the ones that are congruent, that have the same length. Okay? I keep saying same lengths here. Tomorrow we're going to talk about angle bisectors, and everything's going to change. Okay? All right. Let's look at this problem then. This is the problem where we put it all together. This is a triangle. What kind of a triangle? It's an acute triangle. That means, and I'm going to say S is the circumcenter. In your mind, when you are doing these problems and I give you the word circumcenter, you need to tell me that point was formed by what? What kind? This is formed by perpendicular bisectors, which implies what lengths are congruent? So LS is equal to SN, which is equal to MS. That's how you have to approach these problems as you see your terminology. Okay? If I'm telling you S is the circumcenter, I'm telling you that these are right angles. That's what a circumcenter means. If I'm telling you you have a circumcenter, these lengths are all congruent. Right? Look at all that information when you're doing this problem. Put all that information onto your picture so that you can then go forth and answer your questions. Find LS. Well, I just found out that LS and SN and MS are all congruent, right? So is there somewhere that I look to figure out what the length of LS is? Megan. And it's 8 because? Yeah. LS is equal to MS, and so therefore it's equal to 8. Okay, I said find OL. Allie. So 4 over 2, half of that value, 2. Yes. I'm going to put some of this information on here. This is 2, this is 2. All these black ones are 8. What other piece of information can I find or write in here? Isabel?
Well, I'm wondering, is QN 3 or is LN?
QN. I'll do something like this. See how that 4 has that line extending the entire length? That's indicating. So my question is there any other piece of information that I can go ahead and write on here? Lainey? Good. Exactly right. All right, so LN is what? LN is 3 plus 3, which is 6. I would do it in your notes so that you have something to reflect back to because you will be doing a problem like this in your homework. Okay? SQ. Where is SQ? It's a little perpendicular length, right? Do we know how all of the perpendicular lengths are related? No, we only know that the lengths from the vertices to the circumcenter are congruent, right? I'm telling you, you can find SQ. And you're going to have to use some old information. No, no, the height of the triangle would go from a vertex to the other side, forming a right angle. But this length doesn't go continually down to form a right angle. Okay? Claire? And you can use that Y. You have a right triangle. Does everyone see the right triangle? The right triangle that we're looking for, this is SQ, correct? This is my unknown value. What is this length right down here? This is L. Isn't this 3? Yes? And S is our circumcenter, and isn't this 8? Right? That's what we could determine from the picture. That's why sometimes as you find information, fill it in your triangle so that as you get more questions asked, it becomes easier to identify what you need to do. So when you're doing this chapter, you need to remember the Pythagorean theorem is a friend. Anytime you have a right triangle, see if you can use the Pythagorean theorem in some way to figure out lengths. But you have to be guaranteed a right angle. Okay? All right, so then this becomes that x squared plus 3 squared is 64. X squared is equal to what? 55. So x is square roots of 55. You must learn to work with radicals, and they need to be in reduced form. Okay? Not as decimals. Abby? So I want SQ, correct? There's my unknown. Here's my right triangle. Do you see? Or I could have used this side. Either side will give me the same information. Athena? Well, don't go by my picture. Are you saying that the picture is funny? 64 minus 9 is 55. Right? It's 8 is your hypotenuse. Okay, that's fine. All right, one other question I think is what is OS? So OS is another perpendicular length, right? Would you agree? So what am I going to do again? I'm going to use the Pythagorean theorem again, right? And I'm going to say OS is unknown. Hypotenuse is still going to be 8. And my base of the triangle that I want to use is now 2. All right. Okay. Hold on. 8, 2, and this is OS. So this is going to be 64 minus 4 is going to equal x squared in this case. So 60 equals x squared. Square root of 60. No decimals are allowed. Must. Okay. 2 root 15. If we're unsure, we need to factor, if you remember. That's 4 times 15. This is a perfect square, isn't it? So it's 2 root 15. That's the kind of answer that I want. I don't want decimals. Sarah.
Why is it minus 4?
It is x squared plus 2 squared equals 8 squared. A squared plus b squared equals c squared. We're always going to set it equal, Sarah, to the hypotenuse squared. 2 squared is 4. 64 minus 4. I just did the math in my head.
Oh, okay.
Okay. Emma?
So going back to SQ,
Yes. Yeah. Exactly. It's 5 times 11, and neither are perfect squares. Mary? Mm-hmm. You can, although I think you're going to want to draw your pictures and in red determine where the congruent lengths are, and I think that'll take up more space. I would suggest you do it each on a separate note card. Okay? Is that it? All right, one little piece of information. Obviously, it's important. If I'm going to do a little side note here, if I want to square 3x. What do you get when you square 3x? Well, that's why I'm asking. That's why I'm asking. How do I square 3x? Talia? Why? Just keep that in mind when you're doing your homework. Okay? Maybe not today, maybe tomorrow, but it's going to come up.